Hello, good morning everybody. What I'd like to cover today is a couple of the key updates that have happened to the Cortex-M family over the last year or so. The Cortex-M, or the microcontroller profile, was first launched in, I think it was around about 2004, with the launch of the Cortex-M3. ARM has expanded the family to include a couple of lower-end Cortex-M profiles, the Cortex-M0 and Cortex-M0 Plus, and also an enhancement of the M3, the Cortex-M4, which introduced a number of DSP features and hardware floating points. However, about 8 months ago, ARM launched a new processor, the Cortex-M7, which is quite a radically different processor in terms of its hardware architecture and gives a significant performance upgrade to the existing family. So the Cortex-M7 has now been licensed by silicon vendors such as NXP, Microchip and ST, and there is now real silicon available on the market. So the Cortex-M7 really retains the same programmer's model as the earlier Cortex-M devices. So again, if you're familiar with an earlier Cortex-M device, it's very easy to migrate onto the M7. But there are a number of key architectural differences in the CPU, and also a more complex memory model which needs to be understood by the developer. So first of all, the Cortex-M7 inside the processor, the earlier Cortex-M devices had a 3-stage pipeline which had fetch, decode and execute units. The Cortex-M7 now has a 6-stage pipeline which is arranged as 2 3-stage pipelines. This allows a dual issue of instructions, and also the processor is capable of processing different groups of instructions in parallel. So this greatly improves the performance of the Cortex-M7. And fortunately for the programmer, there's no additional complexity in programming. This is all handled by the compiler, so it's really a challenge for the compiler vendors rather than the end user. We just write our C code and we get a big performance boost on the processor. The pipeline also benefits from a new unit called the branch target address cache. So this basically can cache instructions, particularly for looping, so that we reduce the overhead of looping structures. So in sort of marketing speak, this gives us almost a challenge to zero overhead looping, which we find in DSP processors. So again, this just works transparently to us, but it again enhances the performance of the processor. So together we have the dual issue pipeline and the branch target address cache, which if we compare the number of cycles taken for a typical loop on the M4 and the M7, we can see that the number of actual cycles is greatly reduced for the same C code. You just compile it for M4 and it will take over 4,000 cycles, but the same C code compiled for the M7 is just over 1,000 cycles. Plus the Cortex-M7 processor will generally run at higher frequencies than the M4. So for example, the Microchip device is running at 300 megahertz, and new silicon processors for new devices coming in the next few months will take that clock frequency to around about, we're guessing, about 400 megahertz. So again, we'll have devices that have a huge upgrade in performance. Where the Cortex-M7 starts to differ from a user's perspective is that we have a more complex memory model. First of all, the Cortex-M7 introduces a couple of new memory regions called tightly coupled memories. So there's an instruction TCM and also a data TCM. So these are local regions of memory that are, as their name implies, on local buses to the processor, and in a good implementation they will be typically accessed at zero wait states. So we can load a critical code into the instruction TCM and execute at zero wait state, and also critical data can be loaded into the data TCM and again accessed at zero wait state. And here on the data TCM we have two 32-bit buses, so again we can have dual accesses to it. So typically in the instruction TCM we put critical code, interrupt service routines. It would also be possible to locate the vector table and any code literals. For example, if we're doing DSP, you might want to put the DSP coefficients in here to again speed up processing. The data TCM, typically frequently used data, but also be an ideal place for the stack and the heap. While we have the instruction and data tightly coupled memories, these are still limited in size, but we can have the we have a new bus structure which is used to access the on-chip SRAM and the code memory. So this will access slower memories, but to boost that performance for the first time on the Cortex family, there's both an instruction and a data cache located within the Cortex-M7. So unfortunately on here, for some reason, this slide is a little bit wrong. We have the instruction and data cache can be up to 64K in size. So again, both quite large memories within the Cortex-M7. So this gives us a more complex memory. So we have the complex memory map. So with the Cortex-M7, we have the AXI bus, which is a dual issue bus, so a multi-issue bus, so we can have multiple transactions running over the bus. And the AXI bus will allow us to access the processor SRAM and flash. In addition to the AXI bus, there's also a separate peripheral bus, the AHB bus, which is optimized to access the on-chip peripherals. So this will again talk to the AHB bus matrix, which is the same as is used in the earlier Cortex processors, and allow us direct access to groups of user peripherals which are sitting on the advanced peripheral buses. There's also an AHB slave bus as well. So this allows DMA units to transfer data from the chip SRAM and peripherals into the tightly coupled memory. So again, we can boot code or we can boot data into the TCM. So again, more complex bus structures. However, for the programmer, we're still really dealing with a nice linear address space. These are not really introducing complex addressing or paged memory or anything nasty like that. When we're designing a program, we have to be aware of these different memory regions and how we can locate our code and data appropriately to match our application. So that's the real challenge for the developer. So with the instruction and data caches, these are sitting above the AXI bus and can be used to cache the code and data that's accessed over the AXI-M bus. So now we have a memory hierarchy. So with the Cortex-M7, the fastest memory will be available in the tightly coupled memories, followed by the instruction data caches. Below that we have the on-chip SRAM and flash, and then the slowest memories will be external memories. So it's again just understanding this memory hierarchy and how to place code and data. With the instruction caches, where we're the instruction cache effectively, when we enable it, it pretty much looks after itself while the code is executing. However, with the data cache, we're actually caching the internal SRAM or external SRAM of the processor. This may also be updated by the DMA units that will be on the chip as well. So this can introduce coherency issues where we have data that's been accessed by the CPU that's sitting in the data cache. Well, at the same time, DMA units may be updating that in the physical memory. And then we're not getting the up-to-date values, rather we're accessing older data that's in the data cache. So we have, again, issues that we have to resolve as a programmer. The simplest of these are being to switch off the cache, which is often something we might do in the early stages of development when we're getting familiar with the device, but then we're not getting the best performance. We can also, once we've enabled the cache, we can change the different cache policies so that the physical memory is updated whenever we write to the data cache through using a write-through cache policy. It's also possible to control the cache coherency through a number of functions that we'll see in a moment that are provided through the CMSIS standard so that we can invalidate memory or flush memory so that we maintain coherency between the cache and the underlying memory. It would also be possible to place critical or the data that's being shared with the DMA within the tightly coupled memories. So then this memory is shared directly between the CPU and the DMA. So then we escape any coherency issues. So there's a number of ways to deal with the data cache to maintain coherency within the system. So, as mentioned, within the CMSIS standard, we now have a number of functions that are available to directly manage the cache. So for the instruction cache, we can easily enable and disable it. If we want to, we can invalidate the cache, and that will cause cause everything to be reloaded into the cache memory. In terms of the data cache, again, we can enable and disable. We can invalidate the cache so that we write all of the cache data into the system memory, and we can also clean the cache as well so that we can reload from system memory directly into the cache. So we can do that over the full width of the cache, or we can do that by an address and region size as well. So we can finally manage the data that's in the cache. So we have a number of options in how to understand and use particularly the data cache. And we've done some initial benchmarking with the cache and a number of evaluation programs which we'll make available so that you can download these, and if you're interested in using the M7, you can experiment to see exactly how the cache operates within your code. As well as boosting the performance of the Cortex-M family, the Cortex-M7 has also been designed with a number of enhanced safety features as well that make it suitable for use in a SIL3 application. So within the debug architecture, like the earlier devices, there's instruction trace and data trace. So with appropriate tools, this allows you to do performance analysis and code coverage that allows you to fully validate your tool. There's also an instrumentation trace which is very useful for software testing as well. There's also the option to add a memory built-in self-test, though to my knowledge that's not available on devices that are currently on the market. Like the earlier M7s, there's a memory protection unit, or MPU, that again allows us to define a template over the memory which allows different forms of code execution, either privileged or unprivileged execution, access to different regions of code, data and peripherals. So if we want to, we can make a more complex memory map and control what code accesses what region of memory. It's also possible for safety critical designs to have a dual core lockstep arrangement for Cortex-M7 processors. So this allows us to validate the execution of code over dual processors. And again, manufacturers also have the option to add error correction codes to both the cache memories and the tightly coupled memories as well. So this allows us for error detection and correction within the hardware. For manufacturers developing devices, if they want to develop devices for safety critical applications, ARM has also provided a set of documentation that allows them to validate these devices for various SIL level applications. And again, this is available to manufacturers. So hopefully over the near future, we'll start to see devices that have been validated for safety applications, typically automotive or aerospace or medical. As we mentioned, we can have the Cortex-M7 operating in a dual-core lockstep. So in this arrangement, one of the cores runs a cycle behind, so it's effectively checking the operation of the preceding core. If it fails, then effectively we can generate a reset on that. The development tools also have a matching set of safety documentation. So within both the Keil MDK and the ARM DS5 toolchains, there is a fully TUV validated version of the C compiler that allows you to write code up to SIL3. This is maintained and is available with the professional version of the Keil tools and the ultimate edition of the ARM DS5 toolchain. So again, this is a kind of a standard part of the toolchain and not a large extra cost just to get a validated compiler. This also comes with the supporting documentation as well. So it's a very good way to have a safety certified compiler. So the ARM Cortex-M7 and Cortex-R5 are certified for use with ASIL-D and SIL3. The earlier Cortex processors are currently rated for ASIL-B or SIL2 safety development. Now, in addition to releasing the Cortex-M7, ARM have also announced their ARM v8-M architecture as well. So this will be a new generation of Cortex-M processors. So the existing Cortex-M processors are basically split over two earlier ARM architectures, ARM v6-M, which covers the Cortex-M0 and M0+. So this supports the original thumb 16-bit instruction set. And then the Cortex-M3, M4 and M7 are within the ARM v7 architecture, which provides the full thumb 2 instruction set. The new ARM v8-M architecture will consist of a roughly similar split where we have a mainline processor. So this will be the higher performing processors, and then a subset of the baseline processors, which are smaller, lower performance cores, but still within the same architecture and the same instruction set. So the ARM v8 so this will create a highly scalable and much more modular set of processors so that silicon vendors will have a more finely grained choice of the features that they add to the devices. So we'll see a wider range, more configurable group of processors over time. So within the ARMv8M, there are a number of common features. So it's a set of instructions that support load, acquire, store and release instructions. So these have been included to support the latest C and C++ languages. So mainly atomic instructions. Also, the memory protection unit has been updated as well, so it's easier to program and offers a more flexible definition of the regions that we can lay over the memory. And also there'll be enhanced debug capability. Not much has been announced about this at the moment, but I would assume this will add more features such as on-chip trace to the debug architecture. So, for example, on the Cortex-M0 Plus, we have the micro trace buffer, which allows us a snapshot trace buffer with very low-cost tools. So it's easy to see that this will be extended into the ARMv8M architecture. There's also the addition of TrustZone, which is a security architecture for typically IoT type devices, and we'll have a look at that in a moment as well. So in terms of additions for the mainline architecture, there'll be a new floating point processor unit, and also the option to add the DSP instructions without having to have the hardware floating point unit. So at the moment, the Cortex-M4 has the enhanced DSP instructions, but it also has hardware floating points. So you have to have both. In the future, silicon developers will be able to select to have either feature independently. In terms of the baseline features, we have an introduction of the hardware divide instruction, more advanced compare and branch instructions. Interestingly, we've also added the exclusive access instructions. So this really is a step towards supporting multi-core architectures. So the M0 and M0 Plus don't have exclusive access instructions at the moment. So there's manufacturer-specific ways of communicating between cores in a multi-core architecture. The exclusive access instructions will allow us to implement things like semaphores and mutexes in hardware across a multi-core design. Also, we have the introduction of the 16-bit immediate data handling instructions. So this means where we're accessing code literals, these will be encoded into the instruction, and this will allow us to have execute-only memory. So it will be possible to hide things like encryption keys within instruction memory and not effectively prevent people from hacking into the code area to access that kind of critical information. So again, this is quite an important addition for the Cortex-M0s. Also, as designs for M0, M0 Plus are getting larger, the limitation of 32 interrupt vectors is becoming a problem. So the baseline will essentially increase the number of peripheral interrupts that we can handle as well. Also, the baseline is getting the benefit of the 32-bit instruction in 32-bit instructions as well. So this will have something like a 40% uplift in performance for the smaller devices. So again, in ARMv8, the baseline devices will become significantly more powerful. However, I think probably the major addition for the new ARMv8 architecture is the addition of TrustZone for Cortex-M. Effectively, this is a way of creating a protected zone within your application. You can sort of think of this as a container where we can basically put code, data and peripherals that are invisible to code that's executing in the normal mode of the processor. So, for example, if you have a network device and somebody manages to find a vulnerability and can access code within the normal zone, they can't then view any data, code or peripherals that are within the protected zone. So it's kind of like, as I say, a separate processor, a container which this code is running in that's invisible to code outside of it. So we have a new memory or operating model. So like the original Cortex-M processors, we have two different operating modes, a background thread mode and an interrupt handler mode. But now we have two different operating states, a non-secure mode and a secure mode. So we can have functions that are executing in non-secure and functions that are executing in secure mode, and we can construct programs that can simply call between the two operating modes. And in hardware, we transition between secure and non-secure modes. Each mode has its own set of stacks, and it's kind of like two running instances of the same processor, as we'll see. So effectively the programmer's model essentially stays the same. So we have the same register file, but now we have two different sets of stacks, one for the non-secure mode and one for the secure mode. So we have a main stack pointer and a process stack pointer for secure and non-secure. And also interestingly, there are stack limit registers as well, so we can police the size of the stack usage as well. There's also a non-secure and secure control register. So this allows us to set up the different operating modes and the stack configuration for both the secure and non-secure modes independently. So in addition to the central register file, we also have an additional secure memory protection unit, a secure SysTick counter, a secure system control unit, and a new unit called the security arbitration unit, which is used to pretty much like a memory protection unit to define regions of the device which are going to run in secure mode or non-secure mode. So when the chip starts up, it will be running in secure state. So here we'll have a full view of the chip. We can see all the regions of RAM, all of the peripherals, and all of the processor peripherals. However, the security once we've booted, we'll use the security arbitration unit to define which regions of the memory are secure and non-secure. And then we can jump over into the non-secure state, and here we have a reduced view of the chip, so that we can only see the code, data and peripherals that are available to the non-secure area. Anything that's labeled as secure is now completely invisible to us. So as we're executing code, we can be running in the non-secure state, and we can call a secure function as we would normally. So we then branch to the secure function. However, the first instruction in that function must be a new instruction which is called a secure gateway instruction. So this is the entry point into the secure state. If we try to execute any other instruction, we will just raise a security exception. So we must enter by this security gateway. Then we can execute the code in the secure state, and then we have a new return instruction, so we branch exchange back to the non-secure state. And there's also some additional work going on under the hood here, so that if somebody tries to spoof the return address and we return back to an area of code that isn't in the non-secure state, again an exception will be raised. So we have to enter the correct way and exit the correct way, otherwise we trip the security. Similarly, when we're running in secure state, we can make a call to the non-secure state. When this happens, all of the data in the secure state is hidden, and a special code called a function return code is put in the link register, so that once we come to the end of the non-secure function, again we'll do a branch back on the link register. It will see this special instruction, and then we'll unstack from the secure stack rather than the non-secure stack. So there's no bleeding of data across the secure non-secure boundary. So again, so all of our code is hidden. Now, we've said that we have these two different operating states, the non-secure state and the secure state. And we have our special entry point called this secure gateway instruction. Now, this is an opcode, which is a binary pattern, and it would be possible that there could be a code constant that would be in the secure state that had a matching binary pattern. And this would create a false entry point that could be exploited by somebody trying to hack your code. So for this reason, there is a separate, an additional intermediate state called the non-secure callable state, which is where all of the secure gateway instructions must reside. So this would be a much smaller region, so it's typically a branch table, so it would be much easier to examine it to make sure that there are no spurious secure code constants that look like a secure gateway instruction. So when we branch from non-secure into secure state, we must first enter this non-secure callable state, which holds all of the entry points, and then we enter into the secure state proper, execute the code, and then we can return back. So again, this intermediate state simply provides an additional level of security that prevents us accidentally having false entry points. It's also possible to manage interrupts, so we can be running in secure state or non-secure state, and in either of those operating states we can respond to non-secure interrupts or secure interrupts. And indeed we can call functions between interrupts as well. There's no overhead in this, except if we're running in secure state and we have to respond to a non-secure interrupt. Then we have to stack all of the registers that are sitting in the central register file running, so none of the secure data is visible. And then we can run the non-secure interrupt. So this adds a few cycles overhead, but again, it's not a major delay in responding to the interrupt. So now on our vector table, in the secure mode we have an additional exception, which is the security fault exception. So we have any violations of our security will generate an exception, and we can go through to security fault handler and decide what to do. Now, if you want to use the ARM v8M, the existing compiler tools will be able to generate code and execute on the new Cortex processors. However, if you want to use TrustZone, that introduces some new instructions, so you'll need an upgrade to your compiler. Currently, as far as we're aware, the only compiler available is the new ARM compiler 6, which is a new generation of the ARM compiler, which is based on a newer compiler technology, Clang LLVM. So this gives us better code optimization, but will also allow us to generate code for the new ARM v8 architecture. So if you are going to use TrustZone, then you will need an upgrade to your compiler. Also, the development tools, particularly the Kyle MDK-ARM, has been developed to support the new ARMv8-M architecture. And if you install the beta release of the CMSIS support from ARM, inside there is a simulation model for the ARMv8-M architecture and also a demonstration of the TrustZone, a simple TrustZone program as well. So it's possible to run code and see the secure and non-secure operation and how a program is structured to sit on the processor. Also, code generation is possible for execute-only areas of memory as well. So we can expect to see new processors with ARMv8-M, the TrustZone model, probably towards the end of this year, maybe early next year. But already the tools are in place for that, so we should be able to demonstrate these processors as soon as they're available. So I hope that's been useful for you today. If you do have any questions, please let us know and we'll respond to those by email. And thank you very much for attending this webinar today.